Alright, greetings and welcome to the podcast on the four laws of thermodynamics. I whittled this down substantially, but it's still going to be slightly long. I'll try to get through it pretty quick though. Alright, so there are four laws of thermodynamics, and I am going to give them to you in the order they were discovered in, but in the rest of the podcast we're going to go, through them numerically. So the second law was actually discovered first. The first law was discovered second. The third law was discovered third. And what about the fourth law? What do you think? Oh, you'd be wrong. It's called the zeroth law, and it was discovered fourth. Haha. So about the zeroth law. If objects A and B are the same temperature, and objects B and C are the same temperature, what does this say about A and C? Then obviously objects A and C are the same temperature. Now, for all you math heads out there, just the transitive property of mathematics. If A equals B and B equals C, therefore A equals C. Just the property of mathematics, but we're talking about temperature here. Same thing. So two systems, a little more formal definition. Two systems individually in thermal equilibrium with a third system are in thermal equilibrium with each other. And when I talk about thermal equilibrium, I'm talking about two systems that there's no heat flow between them when they're brought into contact. There's no transfer of the heat energy. And remember, temperature is the indicator of thermal equilibrium in the sense that there's no net flow of heat. So if they stay the same temperature, then they must be in thermal equilibrium. No temperature rising, falling, etc. So that's the zeroth law. Now on to the first law. First law, the total sum of all the energy in an isolated system will never increase or decrease. Sounds pretty similar to stuff we talked about when we talked about, mechanical energy. Because it's basically just a restatement of the law of conservation of energy. Like no energy is created or destroyed, it just transforms into other things. So just like potential changes into kinetic, and then kinetic back into potential, it's all the first law of thermodynamics is saying. A little more formal, the internal energy of a system changes from an initial value, Ui, to a final value, UF, due to Q and work. So the equation for that, delta U, remember this delta means final minus initial, so the final internal energy minus the initial equals the Q, the heat, minus the work. So this is where you might run into problems in the problems. Q is positive when the system gains heat and negative when it loses heat. So you got to be careful with the signs on Q. Same with W. W is positive when work is done by the system and negative when the work is done on the system. So when work is leaving the system, it's positive. When it's coming into the system, it's negative. So here we have the system, work going out. Therefore, we have positive work over here. And over here, work's going into the system, so it's negative work, negative W. Just be careful with those. In both of these, heat is going into the system, so what do we say that was? The system is gaining heat, so therefore, these are all positive heats. Positive Q, positive Q. Now, I'll show you why it's important to keep those signs. So those last two figures illustrate a system and its surroundings. So in part A, the system gains 1,500 joules of heat from its surroundings and gains 2,200 joules of work. And 2,200 joules of work is done by the system on the surroundings. In part B, we're still gaining the same amount of heat, but this time the work is done on the system. So in each case, we want to find the change in internal energy. So it's pretty easy to find, just got to remember those positives and negatives. So we had positive heat because heat was going into the system for part A. If you remember what part A looks like, it was that. So positive heat, positive work. We have positive heat minus our positive work. We end up with negative 700 joules. Now part B, the work was going the other way. So we got to have a negative 2,200 joules in there. So in this case, we get 3,700 joules for the part B picture. So part B and part A. Gotta watch those negative signs. Just a quick little multiple choice question for you. A gas is enclosed within a chamber that is fitted with a frictionless piston. The piston is then pushed in, thereby compressing the gas. Which statement below regarding this process is consistent with the first law of thermodynamics? A. The internal energy of the gas will increase. B. The internal energy of the gas will decrease. C. The internal energy of the gas will not change. Or D. The internal energy of the gas may increase, decrease, or remain the same, depending on the amount of heat that the gas gains or loses. Now, if this was a multiple choice test, you would obviously pick D, just because it sounds more scientific. But it's correct, too. So it all depends on how much heat we're putting in there, or how much heat's giving off. I think I have some slides with some pistons here coming up. I'll show you why. Must be in a little bit. All right, so we can't really tell if the internal energy increases, decreases, or remains the same. It all depends on how much heat is going into that system or how much heat is given off by that system. So if we have a cylinder with a piston, if we put some heat in, it's obviously going to increase the energy, so plus U. But if we have heat going out, we're going to have minus U, and this piston's going to go down. And if we have plus U, the piston's going to go up. All right, and the second law, the heat flow statement. Heat flows spontaneously from substance at higher temperature to substance at a lower temperature and does not flow spontaneously in the reverse direction. This is pretty obvious. If you have two things, one's hot, one's cold, you put them next to each other, the hot's going to heat up the cold. It's not the cold sucking heat from... The cold isn't going to go into the hot. The hot only goes to the cold. So hot to cold, not cold to hot. Hot to cold, not cold to hot. Basically all the second law says. So if two objects are not the same temperature, then heat will always flow from the high to the low temperatures. Hot object will decrease in temperature and the cold object will increase in temperature until they both reach thermal equilibrium. So until we get to that thermal equilibrium. Second law also deals with entropy. Entropy is randomness. In essence, it's a disorder. It's spread out, lack of structure, messiness, probably like most of your rooms at your houses. So the second law says that entropy must always increase unless controlled by an intelligence. And I don't mean, it could be aliens, but it's usually, us changing entropy. But entropy in the universe always increases. Us humans and other sentient beings can actually make it decrease. That's how the heaters in your homes work. It's how your refrigerators and your air conditioners work. I didn't include that on this podcast because it would make it like 96 billion slides. So if you really want to know about it, there's a little write-up in your books, or you can just ask me. So entropy increasing means that these machines, like your cars, your air conditioners, can never be 100% efficient because something is always given off. In nature, this entropy is increasing. It's always getting more disordered. And it also means heat flows from hot to cold. So examples, what happens to these things if just left alone? So if I had a stack of wood just sitting out in the forest, what would happen to it eventually? Over time, you'd have pretty little stack of wood, try to get warm for winter. All stacked nice and neatly. But over time, it would just get all disordered. Now, in nature, you never see anything go from like unstacked to stacked. That just doesn't make sense. There has to be some kind of intelligence doing that. And one you're probably most familiar with, what would happen to your bedroom if you just left it alone? You'd have shoes everywhere. You'd have, gum wrappers. I don't know, kids still chew gum these days. You have soda cans because, you can't drink anything else, spilling everywhere. And your parents would also probably get pretty pissed off. So rooms are entropy. So in physics, this capital letter S stands for entropy. Can't use another E because E is energy and stuff. And it's equal to our heat divided by our temperature. So the internal energy divided by the temperature. Remember, internal energy, heat, same thing. Divided by the absolute temperature, so whatever the temperature ends up at. And it's measured in joules per K. So you get joules per Kelvin. You can also do it joules degrees C too, since they're equivalent. Actually, no, you can't. You might see it like this, but usually it's going to be joules per Kelvin. Here's the pistons. So this system starts with the same pressure and temperature on both sides. Then heat is applied to the left side, so we put a flame under here. A green flame, must be a copper flame. And this side heats up. Which way is this boundary going to move? And what happens to the pressure on this side when it's heated? So the boundary will move and the pressure will even out. So this side, the pressure goes up. So P up. Boundary moves this way because of that pressure, until these pressures become equal. Eventually this P over here is going to equal this P over here. So P1 will equal P2 eventually. And at the same time, the unequal temps will affect each other too until they're equal. So all this hot over here from our laws of thermodynamics, the heat is going to flow into the cold, warm it up. Now eventually it's just going to look like this. Everything at the same temperature, everything the same pressure, and our piston ends up over here. So this is very basic principles of how your cars work. We heat up, one side of the piston pushes up, piston comes back down, and so on and so forth, and it turns gears and other stuff in your car to make them move. So just like your messy room, the entropy is a measure of disorder. In this low entropy state, there will be a net force, since there is more movement to the right than to the left. So we know it's going to move this way, so it has low entropy. If there's low entropy, there's going to be a net force. Something's going to be moving. But in this high entropy state, there'll be no net force, since there's no random particle motion. Nothing's moving around. Nothing wants to, spread out. So everything's equal. Pressure here is equal pressure here. Temperature here is equal temperature here. There's nothing flowing, so there's going to be no net force. And we say this has a state of high entropy. So can I get any more work out of these things? Yeah, I need to find a third gas sample at a lower temp. So I put, another gas over here with a lower temperature, and the piston would come this way until it all evened out again. And then, or I could just supply my own energy and create another temperature difference, which is how your cars work. You keep burning gas to make temperature differences that keeps this piston moving back and forth. So entropy, measure of how evenly spread out. So the more evenly spread out, the higher the entropy. Entropy is a measure of energy that is no longer useful or workable. It's called reversible. If you can't reverse the process, then it's a high entropy state. So work is change in energy. We already knew that from our previous chapter. And it won't change anymore if it's spread out evenly. You can't get any more work out of that energy if it's spread out everywhere. You don't have a higher energy in one place than another. So just like if I let a marble go on a curved track, it's going to go potential to kinetic, kinetic to potential, but it's going to keep getting. So this ball is going to start here, it's going to come over here, but then it's only going to reach this high, then eventually going to reach this high, so on and so forth, back and forth, until it just stops there in the middle. So that's its final state. The energy is all spread out. So we can't get that to change anymore unless we do something else to it, unless we pick it up again or put a little motor on the ball. But in this state down here, high entropy, because it's all the energy is evenly spread out. So the amount of work done or the efficiency of an engine is determined by the differences in temperatures. So I'm just going to show you why it's better to drive your car in the winter. So if you have a hotter engine and cooler water, it makes for a greater temperature difference, so you get more work done. So the hotter your engine and the cooler your water in your radiator, the more efficient you can make your car, and less gas you're going to burn. This means more work will be generated from an engine, and the engine will run more efficiently. So let's say when the temperature differences are the greatest. So these are just some random temperatures. So if your car is at 2000 Fahrenheit, the metal on your engine is 800 Fahrenheit, your oil is 300, the water is 150, and the air is 70. Now if you can change these temperatures, so like we'll keep this 2000, but hey, it's like 14 degrees outside because we're in New England in wintertime, you're going to get more temperature difference, which means you're going to have more efficient engine. So your cars are actually more efficient in the winter than they are in the summer. So the greater these temperature differences, the more energy from the car engines. All right. So let's say we have 1200 joules of heat flowing spontaneously through a copper rod from a hot reservoir, so T hot, temperature hot, 650 K, to a cold reservoir at 350 K. Determine the amount by which this irreversible process changes the entropy of the universe, assuming that no other changes occur. So now we have a temperature difference, 650 K, 350 K. This is actually how refrigerators and heaters work. And a piece of rod connecting them that does 1200 joules, allows 1200 joules of heat flow. So the entropy of the universe is going to be equal to the entropy lost by the hot reservoir, which is negative, so we know it's lost, plus the entropy gained by the cold reservoir. So entropy lost by the hot plus entropy gained by the cold. So we have the 1200 joules, which is the energy that flows out of the hot, divided by the temperature of the hot. And then the 1200 joules flows into the cold, divided by the temperature of the cold. So we do that in our calculators, and you get 1.6 joules per Kelvin. These are actually pretty easy processes to work with, or pretty easy equations to work with. So any irreversible process increases the entropy of the universe. And I'm just going to state the second law of thermodynamics in terms of this entropy real quick. The total entropy of the universe does not change when a reversible process occurs. So if it's a reversible process, we can go back and forth. The entropy of the universe does not change. But it increases when an irreversible process occurs. So this change in entropy is always going to be greater than 0 if it's an irreversible process, but it equals 0 for reversible processes. So if entropy is randomness, which one of these is more random? Here we have nice, orderly, stacked bricks. And over here, we just have a pile of bricks that fell over. Now, obviously, A is more ordered than B, so B is more random. So the second law of thermodynamics says that nature always goes from order to disorder. So something that looks like this will eventually look like this. Now these rocks start breaking down, or something might run into them, and it's always going to go from here to here. It's never going to go from here to here. That'd just be crazy. So in nature, do you move from A to B or B to A? Obviously you move from A to B. A to B. Never go the other way. Never, 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 never. Okay, and another example. Which is more disordered, the glass of ice chips or the glass of water? Now this looks kind of crazy, you got just chunks of ice everywhere. But this one all depends on what you're talking about. So if I'm just talking about the large scale, the ice looks more disordered. It looks like it's everywhere. But on the small scale, the solid phase, severe limits where molecules could be. So like all these little ice molecules are close together. A different color. So over here, the molecules are very ordered in each of these ice chips. And you get nice stacked. But over here in the water, they're just everywhere. So on the small scale, the ice is more ordered. On the large scale, the ice looks more disordered. So ice crystal molecules are much more ordered than free. Yeah, I already said that. Okay, just another easy problem. Find the change in entropy that results when 2.3 kilogram block of ice melts slowly. We can reverse this process so the entropy in the universe does not change at 273 degrees K or 0C. So we have to use our formula for Q with the latent heat of fusion. I think in your book they use HF. You might see LV or LF. It means the same thing as HF or HV. So mass times the heat of fusion for water divided by the temperature of it. So 2.3 kilograms times our HF of water divided by 273 K. And you get an entropy of 2.8 times 10 to the 3 joules per K. Quick little multiple choice. 2 equal amounts of water are mixed together in an insulated container. The initial temperatures of the water are different, but the mixtures reach a uniform temperature. Do the energy and entropy of the water increase, decrease, or remain constant as a result of the mixing process? So A, both increase. B, both decrease. C, energy of the water remains constant, entropy decreases. Or D, the energy of the water remains constant, and the entropy increases. Now we know that we're not putting any more energy into the system. It's just allowed to come to equilibrium. So that means B and A are gone. And time is moving on, and the nature of particles is to tend towards entropy, to increase entropy. So that means D has to be correct. Entropy increases, energy stays the same. When scientists talk about entropy, they also a lot of times refer it or equate it with time. So Newton's laws, they work forward and backwards. Momentum, simple harmonic motion, equal and opposite reactions, all these principles we can reverse. However, the increase in entropy isn't reversible. An increase in disorder is the only way to tell forwards from backwards, because we can't go from disorder to order. So we know time is moving forward if something goes from order to disorder. That's where time comes into play. We know something gets more disordered over time, so the more disordered something becomes, the more time must have passed. So which came first? Obviously, this guy came first. We moved from order to disorder. And if we were playing a game of pool, we know the balls must be moving out like this. Balls have to be going away because we know as time increases, things don't get more ordered, they get more disordered. So obviously, the balls have to go out from the center. All right, almost done. Restatement of the second law. States where energy is not spread out evenly will evolve into states where energy is spread out more evenly. This simple little statement actually has a very big impact on the future of everything we know. So right now, we have planets, there's Earth, we got stars, all this. All of these things are pretty ordered. If things weren't ordered, we wouldn't be here. But as time goes out, all these things start breaking down. All these molecules start getting evenly spread out. All the energy is evenly spread out. Until the entire universe, all the matter is evenly spread out. I mean, nothing exists because everything shares the entire realm of space equally. Now, this is one of the views on what's going to happen at the end of time, that all matter is going to be evenly spread throughout the universe. Nothing's going to exist. It's just, this big amalgam of, everything evenly spread out. And here's the third law of thermodynamics. Absolute zero is a state of zero motion. This means there's absolutely no entropy. You can't go from order to disorder because there's no motion. You can't, nothing's moving, nothing's changing. And we know that entropy has to increase over time, so this state of absolute zero can never be reached. And that's all I'm saying about the third law. That's all you need to know. Adieu.